Hello AP, this is Mrs. Sargent, and this is section 19.2. So it's not from chapter 12, but it does have to do with kinetics. So this is the kinetics of radioactive decay. Every radioactive sample has a decay rate or amount of particles that will decay over time. This is a first order process, and so this is going to be a derivative of the first order integrated rate law that we nicknamed the Naudi-Katie equation. So the derivative of that is the rate is equal to negative the change in your N, which N is your radioactive nuclei. Divided by the change in your time is equal to K, your rate constant, times the radioactive nuclei. So half-life is the length of time required for the concentration of a reaction or of a reactant to decrease to half of its initial value. So for first order processes, the equation that we're going to use to find that half-life time is T1/2 is equal to 0.693 divided by your rate constant. Now, last year we did do some work with half-life and determining the initial and the final amounts and that sort of thing. But one thing we never did is we never solved for the half-life time, and we're going to do that today. So a fast reaction with a short half-life is going to have a large K. Now, remembering that the equation T1/2 is equal to 0.693 divided by K. So if we want this value to be small, we need to have a large K, which means it's going to decay in half faster. For a slower reaction with a long half-life, so this is a bigger number, then we're going to have a smaller K, a smaller rate constant. So this example, the decomposition of SO2Cl in chlorine is a first order reaction. So we're told that it is first order. The rate constant is 2.2 times 10 to the negative fifth, 1/2. And it occurs at 320 degrees Celsius. We want to determine the half-life of this reaction. So T1/2 is equal to 0.693 divided by the rate constant. So since we know the rate constant, we can just plug this straight into the equation. 2.2 times 10 to the negative fifth over seconds. And when we do that calculation, we get 31,500 seconds. Now we have 3 sig figs and 2 sig figs, so I am going to round this to 32,000 seconds for the final answer. In this next example, the decomposition of N2O5 dissolved in CCl4 is a first order reaction. The chemical change, we have 2 moles of N2O5 decomposing to 4 moles of NO2 and 1 mole of O2. This happens at 45 degrees Celsius. The reaction has begun with an initial concentration of N2O5 of 1.00 moles per liter. After 3 hours, the N2O5 concentration has decreased to 1.21 times 10 to the negative third moles per liter. Now we want to find the half-life. So we know that half-life is equal to 0.693 divided by K. The thing is, in this problem, we are not given the rate constant. So we need to use the initial concentration, the final concentration, and the time in order to solve for K. So we're going to use our first order integrated rate law. To solve for K. So natural log of the initial concentration. I guess I should have used brackets there. Initial concentration divided by the final concentration times our rate constant times our time. So natural log of 1.00 moles per liter divided by the final concentration, which is 1.21 times 10 to the negative third moles per liter. And that is equal to K, and our time is 3 hours. Now, the total time is in 3 hours, but we want to find the half-life expressed in minutes. So I'm going to take 3 times 60 minutes to get our time in minutes, which is going to give us 180 minutes. Now, solve for K. And we will find K is equal to 0.0373 over minutes. This is what K is equal to. So now we can plug this into our half-life equation. So the half-life is equal to 0.693 divided by 0.0373, and that is going to give us a half-life of 18.6 minutes. So remember, whenever you're looking at a problem, look for the information that is given to you and what you're trying to find, and then figure out how you need to work the equations to find that answer. So here is another example using half-life. It says the radioactive decay of thallium-206 to lead-206 has a half-life of 4.20 minutes. And starting at 5.00 times 10 to the 22nd atoms, we want to calculate the number of atoms left after 42 minutes. So we are given our half-life time, and then we're giving our starting amount. We want to find the final amount. So we are going to use both the half-life equation and the first order integrated rate law, because one thing that is not given to us in this problem is we do not know what K is. So we need to solve for K. So 0.693 divided by K. That's our equation. We know the half-life time, 4.20 minutes. Is equal to 0.693 divided by K. Solve for K. And we find that K is equal to 0.1651 over minutes. So now we can use the first order integrated rate law in order to solve for how many atoms remain. So the natural log of our initial amount divided by our final amount, which is what we're trying to find, is equal to KT. So our initial amount is the 5.00 times 10 to the 22nd atoms. We do not know what our final amount is. we found K to be 0.165 minutes, and our total time is 42 minutes. So in order to solve this, to get rid of our natural log, we're going to need to use E to cancel out the natural log, take the E of both sides. So we get 5.00 times 10 to the 22nd over our final amount. And then we need to solve for that final amount. No. Sorry, my dog is barking at the neighbor's dogs. So solve for there. And we are going to find that our final amount NT is equal to 4.89 times 10 to the 19th atoms. That is our final amount. And this problem says a freshly isolated sample of Y90 was found to have an activity of 9.8 times 10 to the 5th disintegrations per minute at 1 p.m. on December 3rd, 1995 at 2:15 p.m. on December 17th, 1995. Its activity was redetermined and found to be 2.6 times 10 to the 4th disintegrations per minute. Calculate the half-life of Y90. So we aren't given a specific time, but we are given the time frame. So December 17th from December 3rd to December 17th, that is going to give us 14 days. But we're not taking this at the same time. So 1 p.m. to 2:15, that's 1 hour, 1.25 hour. So total time is going to be in hours 337.25 hours. Now it does say disintegrations per minute, but that's just looking at the concentrations or the amount of radioactive nuclei in that time. We don't need to convert this to minutes. So now we can take the natural log of our starting amount, which was 9.8 times 10 to the 5th, and divided by our final amount, 2.6 times 10 to the 4th, is equal to K times our time. We can't jump straight to the half-life equation because we did not have our K constant. So the T1 half is equal to 0.693 divided by K. We have to find what our K is before we can use that equation. So that's what we're doing here with the first order integrated rate law. So go ahead and pause the video and solve this. Welcome back. We found that 1.1 times 10 to the negative second, 1 over hour is our K. So then we can plug this in here And we are going to find that our